Hello, this is the second lecture on kinematics. It is basically a continuation of where we left off from the first lecture, where we started on covering the kinematics in one dimension. In this lecture, we will continue on with that, and we will be presenting the equations of kinematics. So let's get down to it. The equations of kinematics are basically three equations that allows you to calculate the position or velocity of an object in future time or in the past. Okay, so let me displace them for you, and then we will solve some basic problems on how to use them. So here they are, and this is basically my version of how to write them. So, or my notation for it. V equals V naught plus AT. V squared equals V naught squared plus 2AX. And X equals V naught T plus 1/2 AT squared. Okay, so these are collectively called the equations of kinematics, and I like to number them equation number 1, number 2, and number 3 in this particular order. Okay, like I said, these equations are equations that allow you to predict the velocity. For example, look at, let me put a different color. For example, given the initial velocity and the acceleration of the object, what is the future velocity of the object after some certain amount of time, t? You see what I'm saying? Or the same thing here, except that this equation does not contain time, as you can see, but it contains displacement. In other words, given the initial velocity and the acceleration, how fast the object is going after it travels some distance x. You see what I'm saying? This one, we have the displacement here, or the distance traveled by the object. So given the initial velocity and the acceleration, how far it will go after a certain amount of time, t. You see what I'm saying? And so on. Okay? So you can think of them as an evolution equation where they allow you to predict or retrodict the evolution or the motion of the object as it is moving along in a straight line, for example. Okay? So collectively, we call them, as I said, the equations of kinematics. Of course, I urge you to memorize them because you will be using them extensively in this course, whether you take this course or the next one, and for your future engineering courses. So definitely, I would advise you to commit them to memory and memorize them once and for all. Okay, one more thing about them. So which one is a better equation to use? Well, they're all equivalent, and each of them has its own flavor. For example, if you look at the first equation, it has final velocity, initial velocity, acceleration, and time, but it doesn't give you distance, for example, x. The second equation gives you distance x, it has acceleration, it has initial velocity and final, but it doesn't give you any information about the time, t, okay? This one, the third one, it gives you information about the time, acceleration, initial velocity, and displacement, but it doesn't give you information about, say, the final velocity, and so on, okay? So basically, when you read a problem and you are asked to find something, just write down what's given, and then you look for what's the best equation to use to to solve for whatever you're solving for. So let me give you an example. Oh, let me show it to you first in print. How does it look like in your textbook? How do they look like? And this is, I just made a screenshot of those equations from the textbook. I'm trying to make it small. There it is. As you can see, these are, I think they're arranged, the order is different, but anyway, look at that. So when I don't, well, the initial velocity for me, I call it the naught. So I put a little circle on there underneath that. That means initial velocity. The book uses V sub is. I don't even know what S stands for. I'm not sure. And then you have the final velocity. I don't put anything there, the subscript. There's no subscript. He uses V sub fs. And then you have the time is delta t, he's calling it. I call it simply t. The displacement, mine is called x. He calls it delta s. and the acceleration a sub s. He's obsessed with this s. He keeps writing it. I don't know what it is. Anyway, got it, everyone? Okay. Let me give you an example. Oops. Suppose, I'm copying it here from my notes. Suppose that we have a car. So let's say this is the road right here, okay? And I have a car, here it is. And the car, he says, we have a car traveling along a straight line, and with a speed of initial speed v naught is equal to 15 meters per second, okay? Now at t equals 0, I'm reading the problem here from the notes. At t equals 0, the car begins to accelerate, okay? So car accelerates at the rate of a equals 2 meters per second squared. Okay, this is the rate of acceleration in order to pass a truck. Okay, now he's asking what is the velocity of the car. So what is the velocity of the car after 5 seconds? Okay, so let's go back. So basically what you have a car. Okay, here's the car initially moving at 15 meters per second, which is about 30 miles per hour roughly, on the road at constant speed. There is a truck along the way. The car, the driver pushes the accelerator to pass the truck. So as he or she pushes on the accelerator, the acceleration rate of that car becomes 2 meters per second squared. So it moves and it passes the truck. After 5 seconds, what is the new speed of the car? You got that? Okay. So how do we solve something like this? Again, always keep an eye on your kinematic equations. Please take the time to write them down right now, because I'm going to make them disappear and we'll be working on them without looking at them. So please write them down somewhere. Again, you can also your advice to commit them to memory. So anyway, so what's given to us here? So we have here the initial velocity of the car is 15 meters per second. The time is 5 seconds. He said, what is the new speed after 5 seconds? He's looking for the final velocity, and he also gives us that the acceleration is 2 meters per second squared. Okay, so what would be the best equation to use? Looking at kinematic equations, you want to go for a kinematic equation that contains v. So I have the second equation right here and the first equation. However, the second equation expects you to have the distance traveled by the car while accelerating. We don't have that. You see what I'm saying? But the first equation here, you have pretty much everything, and then you will be able to calculate the velocity. So I'm going to use the first equation here. So let me move the screen up. So we have here the kinematic equation says v equals v naught plus at, and I just substitute everything. So the initial velocity is 15 plus 2 times 5, and that will be 15 plus 10, and that will be 25 meters per second. That's about something like 45, 50 miles an hour. Okay, and there we go. This is the new velocity of the car. Got it? Okay. The second part, this is for the first part. Let me just... this is part A right here. Part B of the problem, the part B says, calculate how far the car traveled. So how far car traveled in 5 seconds. Okay, so we calculate what's the speed of the car after 5 seconds. Now he wants how far the car will travel after 5 seconds. Well, again, we go back to the kinematic equations. Probably which one would you like? I can use equation number 2 and solve for x, or I can use directly equation number 3 and just plug it in. Would I get the same answer? Absolutely. Let me show you. So let's use both of them, okay? I want to show you both of them, and show you that you will get the same answer anyway. So let's start with equation number 2. So equation number 2 says v squared equals v naught squared plus 2ax, and x is equal to, in this case, v squared minus v naught squared over 2a. A piece of advice: always solve for the variable without plugging in the numbers. Okay, so first solve a variable in the symbolic equation, then you plug in the numbers. So anyway, so we have that. This is the value of x, so I can just plug in my answers. So the v squared here, basically 25 squared right there. So that's 25 squared minus v naught squared is 15 squared, is that right? Divided by 2 times a, the acceleration, I forgot what it is. What is it? 2, right? So we have the acceleration is equal to 2. And then when I calculate that, so let's calculate this. I hope you are calculating things with me. So that would be 25 squared. So we have here 625 minus 15 squared is 225 divided by 4, right? So we have divided by 4, answer 100. So according to my calculation, the car has traveled 100 meters, all right? Another way of doing it, another way is to use the kinematic number 3, which says x equals v naught t plus 1/2 at squared. We should get 100 as well. So anyway, so we have v naught, and that's 15 times 5 seconds plus 1/2. A is 2. 5 is, t is 5 squared. So in this case, we have 15 times 5, and that's 75, plus 2's cancel out here. We end up with 25, and that's again is 100 meters. So there we go. So I have that the car traveled for 100 meters while it is, or it was accelerating. You got it? Okay. All right. One more problem. So that's basically how you solve a basic kinematic equation. We're going to be doing some harder ones later on. Let me do one more for my notes here. That's okay. Okay, here's another example. So here you have the following situation. You have we have a car moving at constant speed of 30 meters per second. Okay, that's about what, 65 miles an hour. So basically double the meter per second will give you approximately the miles per hour, roughly, not exactly, but that's how you get a feel for it. 30 meters, just double it, so double it and a little bit more. So maybe around 65, 66 miles per hour. So it's pretty high. So, okay, so we have a car traveling at the speed of 30 meters per second, passes a trooper at rest. The trooper is at rest. Okay. 1 second after the car passes, the trooper means police, right? The trooper chases the car. With acceleration of 3, let me just write it down as a A equals 3 meters per second squared, okay? The question is, how long does it take the trooper to overtake the car? Does it take the trooper to catch up with the car? How about that? Catch up with the car. Okay? So here we are assuming that initially the car is moving with constant speed. Remember that, okay? So let me just write it down here, so we both agree on that. So the car here is moving constant speed, okay? Why do I emphasize that? Well, constant speed, that means the acceleration is 0. You see what I'm saying? The acceleration of the car, not the trooper, is 0. So the equations of kinematics, really all of them expect that acceleration don't really apply exactly. Okay, so what do we have here? So we have the car. It passes the trooper with a speed, constant speed of 30 meters per second. After 1 second, it says here, so the trooper, remember, it's at rest. So after 1 second, the car passes the trooper. So the trooper chases it with this acceleration, okay? So by the time the trooper begins to move, the car has already traveled for 1 second. The question is, how far did it travel until the troopers start catching up with it, okay? And that would be equal to what? That would be equal to the car is going, V naught is equal to 30 meters per second for a time of 1 second. So the distance traveled by the car initially is basically V naught t. Make sense? So that will be 30 times 1. So that will be 30 meters. So in other words, when the trooper started to move, the car is already 30 meters ahead of him. You got it? Okay. And then the trooper is, now it's accelerating until it catches up with the car. The question is how long? Well, now, by the time the trooper catches up with the car, they both have traveled the same distance. Make sense? By the time it catches, like they both have, in other words, the distance traveled by the car, I'm going to call it h sub car, is equal to h sub trooper. By the time the trooper catches up with it. So this is where the key for solving this problem is that the distances here traveled would be the same. So what is the distance traveled by the trooper? Well, we can use kinematics. Remember, the trooper started from rest. So we go back to the third kinematic equation, which is right here. Write this one, number 3. And we're going to put it for the trooper. So that's going to be V naught t plus 1/2 at squared. As you know, the initial velocity of the trooper is 0, so that's 0, right? So basically it is 1/2 at squared. And for the car, well, what is it for the car? Well, the car is the distance traveled by the car. It would be 30 meters head start, the one we just calculated, plus V naught times t for the future. You see what I'm saying? In other words, it's 30 plus 30 t equals to 1/2 at squared. And that's about it. So I'm going to put in my what's given to me, and I'm going to solve for the time t. This is basically what he's asking for. He said, how long does it take the trooper to catch up with the car? So basically he was looking for the time. So I have here 30 plus 30t equals to 1/2 times a is given to us. It's 3 right there, right? See it? Times t squared. And I would clean it up a little bit. I have here 30 plus 30t minus 1.5, excuse me, t squared equals 0. As you can see here, I have a quadratic equation that I can solve. So I'm going to use the quadratic formula to solve for this one. I hope this is understandable. So how do we do it? Well, we know that t equals minus b plus or minus square root of b squared minus 4ac divided by 2a. I hope you memorize that as well. So here we have a is equal to 30. I'm looking at a is equal to negative 1.5, b equals 30, and c equals 30. And we just plug it in for the time. Now remember, if you remember solving quadratic formulas, you always expect to get 2 roots. Remember that? And sometimes those roots, one positive, one negative, and so on. In physics, the situation is a little bit different. Here we're solving for time, and time is always positive. So if you get a negative answer for the time, simply ignore it. Okay, keep that in mind. There is no such thing as negative time. So if you get a negative root, just ignore that. You're not going to get, most likely, you're not going to get 2 negative roots when solving for time. One of them is going to be negative, not always, but a lot of times it will be negative. So you can just ignore that negative root and just stick with the positive root. You get that? Keep that in mind. So anyway, so we have that, and then we just plug it in. So we have minus 30 plus or minus square root of 30 squared, which is 900, minus 4ac. 4a is 1.5 with a minus is right here. C is 30 divided by 2a, 2 times negative 1.5, and then we work it out. And I'm looking at my notes here. I worked it out in details. Let me show you what I've got. And I want to solve the quadratic formula only once, so you can see how I do it. You're going to get 2 roots, like I said. The first one is this one, minus 30 plus 32.9 over minus 3. Okay, if you work out the square root here. Okay, and then the other one is minus 30 minus 32.9 over minus 3. The first one will give you some number that is less than 0, which is, we call it unphysical. Okay, there is no such thing as negative time. You get that? Unphysical. I need to write it better. Unphysical. Okay, and the second one here, you're going to get a nice positive number, 21 second. Okay, so basically, let's go back to the question. He says, how long does it take the trooper to catch up with the car? Well, 21 seconds, right there. So t is equal to 21 seconds. You got it? I hope you did. Okay, good. One more problem. Let me go back to the book. I need to put it within the frame so you can see it. There we go. This one is kind of interesting, the number 18. Let's read it together and we'll solve it. He says a Porsche challenges a Honda to 400-meter race. Okay, because the Porsche's acceleration of 3.5 meter per second squared is larger than the Honda's 3.0 meter per second squared, the Honda gets 1 centimeter, excuse me, 1 second, not centimeter, 1 second head start. Okay, who wins and by how many seconds? Got it? Okay, let me close that. So problem, I'm just going to call it problem number 18. Okay. So we have the following. I'm going to draw my diagram just to show you how it works. So I'm going to draw 2 cars. One represents the Porsche, one represents the Honda. So here is the Porsche right here, is the car, right? and this is the Porsche P, and it's moving like that. This is at x equal 0. Of course, both of them travel a distance of 400, so that's x equal 400 meters. Okay, and the acceleration of the Porsche is given to us by 3.5 meter per second squared. And then we have the Honda. I'm going to draw another diagram pretty similar to this one, where it ends at x equals 400 as well. Okay, so they both travel the same distance, keep that in mind. So here is the car. I draw a car in a funny way, sorry about that. That's the Honda right here, at x equals 0 as well, where the acceleration of the Honda is 3 meters per second squared. However, according to the problem, the Honda is given a head start, right? Okay. So how do we solve this problem? So this is the Porsche right here. Porsche, how do you spell that thing? Porsche, like this, I think. That's the Honda. Okay. So how do we solve this problem? Let me go back very quickly and just make sure that we all understand it. Let me just read it again. A Porsche challenges a Honda to a 400-meter race. Because the Porsche's acceleration 3.5 is larger than the Honda's 3, the Honda gets 1 second head start. In other words, the Honda is allowed to move for a full second, to accelerate and go for 1 second before the Porsche catch up with it or starts. Okay, so who wins and by how many seconds? All right, so the way we're going to do this is you work out the kinematic equation for the Honda and for the Porsche, keeping in mind that they're both going to travel the same distance of 400, right? So one way to do it is you go like this. So the distance for the Porsche, distance travel for the Porsche, which is 400 meters, is equal to, according to the kinematic equations, v naught t plus 1/2 a t squared, where a here is for the Porsche. Okay? And the time here, of course, is also for the Porsche. Okay? Now, the initial velocity of the Porsche is 0. So this is 0. So basically, x sub p, which is 400, equals to 1/2 a sub p t sub p squared. I'll come back to this equation in a minute. I can put in some numbers in there, but I'll do that in a minute. Okay, now for the Honda, however, we have something similar, but we are giving the Honda what? A 1 second extra. Okay, so the Honda's x sub h, which is also 400, is going to be equal to v naught t plus 1/2 a for the Honda, the acceleration, but the time here is given 1 second extra, so it's going to be t Honda plus 1 quantity squared. You see how I did that? Remember, the basic kinematic equation is x equals v naught t plus 1/2 at squared. This t for the Porsche is just t. For the Honda, well, we are adding 1 second to it. So that's what I've done here. Okay. Again, the v naught t here is 0 because the initial velocity of the Honda is 0 as well. Okay. Now, what's equal here is that the distance traveled by both of them is exactly the same, 400, 400. So I'm going to equate those two equations together. This equation right here and this equation. I'm going to equate them together, and then I can solve for them. Or before I do that, I can solve for t sub p and t sub h for both equations. So let me take equation number 1 and call that this equation number 2. So take equation number 1, take 1, and so I have here 400 equals 1/2. A sub p is what? Here it is right here. This is a sub p right there, guys. This is h, and it's not all good, h. So it's 3.5, so I'm going to plug it in there. T squared is t sub p squared, okay? And then I can just solve for t sub p. When I work it out, which is 400 times 2 over 3.5, all of that under the root, right? And then when I plug it in, I'm going to get 15.12 seconds. So that's how long it will take the Porsche to travel the 400-meter dash, if you will. Got it? Okay. We do the same thing for number 2. So here we have, come on, it's not moving. So we have here this equation right here. I have 400 equals that. So I have here, let me write it down here. So I have here 400 equals half. A sub h is 3, correct? T sub h plus 1 squared, just like that, okay? And then I would solve for it. By doing the algebra, I will end up with, here is one in the middle, so you're going to get something like this, or T sub h is equal to 15.30 seconds. In other words, the Honda will take it 15.3 seconds, but the Porsche will take it 15.12 seconds. So in other words, the Porsche will reach the 400-meter dash sooner than the Honda, and that means the Porsche will still win. So Porsche still wins. Okay, by how much? By how much? Well, by delta T, which is T Porsche minus T Honda. So you can subtract those two numbers together. 15.3 minus 15.12. So by 0.18, not much, but anyway, there it is. By delta T equals 0.18 of a second. You got that? Okay. There are other methods. I've seen this. This is a popular problem. I see it in different books, and I've seen people solving it in various ways. So this is one way to solve it. There are other ways to do it. Okay, good. One more problem from the book. Here's a problem. You can think of it like a review from the topic that we covered in previous lecture. Problem number 35. I'm going to do 35 and 36 from chapter 2. It says that the position of a particle is given by the function. Remember we talked about the function x of t? So we have a function x of t is equal to 2t cubed minus 9t squared plus 12, where in meters, of course, and where t is in seconds. Okay, so we have part A and part B. Part A says, at what time is the velocity v sub x, at what time v sub x is equal to 0? Okay. So how do we do this one? Well, so he wants to know the time when the particle stops. Basically, that's the meaning of it. Or times could be more than one, maybe. We don't know. So the first thing I need to do is I'm given the distance function or the position function or the position vector, call it whatever you like. It's this one right here. This one right here. So from this, I can get my velocity. Well, velocity is defined as v sub x is equal to the derivative of that, right? So derivative of dx dt. So that will be, 6t squared minus 18t. Is that right? And there we go. So he said, at what time v sub x is 0? So all I need to do is what? Equate it to 0. So make it equal 0 to get that time. So I have here a basic algebraic equation, 6t squared minus 18t equals 0. Let me reduce it, divide both sides, divide everything by 6. So I'm going to get t squared minus 3t equals 0. Take t as a common factor. So I have t minus 3 equal 0. And therefore we have 2 times here. T equals 0 and t equals 3. 3 seconds, that is. 3 seconds and 3 seconds. There we go. So at t equals 0 and t equals 3 seconds, the particle stops. Okay, any other time the particle, I guess, is in motion. Okay, but the particle stops at those times. Okay, all right, that's part A. Part B, he says, what are the particle's position and its acceleration at this time? At those times, this is at those times right here, at t equals 0 and 3, where the particle stops. And what is the acceleration of the particle at that? Well, first of all, let's go back to the x of t. We are given x of t. It's right here. Right there. Oops, where is it? Right here. So I'm going to write it down again. So I have here 2t cubed minus 9t squared plus 12. Okay, and he said, what are the particles' position and acceleration at those times? Well, we go x of 0, so that will be 12 meters, right? And x of 3, you can just plug it in. So you have 2 times 3 cubed minus 9 times 3 squared plus 12. We can calculate that. So that will be 3 cubed is 27, correct? So 3 cubed is 27 times 2 will give me 54 minus, what is it, 81 plus 12. Is that right? And then we can calculate all of that. So I have here 54, I'm using my calculator, minus 81 plus 12. I hope I did it correctly. I get negative 15. So the particle's position is negative 15 meter mark, instead of saying meter mark. In other words, if it is, here is the x-axis, if you will, here is x equals 0, and of course this is x positive here. So it's somewhere here, x equals negative 15 right here. So the particle is located there at this time. You got it? Now he wants to know the acceleration of the particle. Well, we need to get the acceleration. So what is the acceleration? It's the second derivative of the displacement, okay? Or the derivative of the velocity, which is the one we just got. So the velocity is, here is the velocity right here, guys. Without the zeros, right here, okay? So we have 6t squared minus 18t. So that's d dt, what is it? I forgot it already. 6t squared minus 18t. So we take the derivative of that, and that will give me 12t minus 18. That's the acceleration function as a function of time. There it is. So now a of 0 is equal to 12 times 0 minus 18. And that's equal to minus 18 meter per second squared. All right? And a of 3 is, what is it? 12 times 3 minus 18. Is that right? So we have 12 times 3 minus 18, and that will give me 18. So it's 18 meter per second squared. And there we go. That's basically the full solution to this problem. Okay? Okay, good. problem number 36, and then I'll move on to the next topic of this video lecture, and that is free fall. Number 36. It says the position of a particle is given by the function. We have another function here, x of t is equal to 2t cubed minus 6t squared plus 12 meters, where t is given in sect. Okay. Question, part A, it says, at what time does the particle reach its minimum velocity? At what time? V is min. Okay? And part B, I'll come back to it. And part B says, at what time the acceleration is 0. All right? Now, what makes this problem interesting for me is that it requires basic calculus for the first part. The second part is easy. Okay? Let me back up a little bit and just go back to some calculus that we have studied. Okay? So this is just a review here for you. Calculus 1. Suppose I have, remember this is just calculus review. Well, suppose I have a function f of x, let's say, I'll make up something, x squared minus 6x plus 5, for example. Okay? So that's a parabola, right? And it looks something, I'm not sure, it looks something maybe like that. Something like that, right? X, well, I can use the graphing Desmos. Let me do that here. So I have here x squared, what is it? I forgot what it is now. X squared minus 6x plus, or sorry about that, plus 5. And there we go, right here. Okay, there it is. So the minimum value of the function is right there, which is, here we go. See it? 3, negative 4. Do you see that? You see the 3, negative 4? When I move it, it kind of disappeared, but it's right here. Okay? So now let's read the same question for this problem. He says here, at what time the velocity is minimum? I'm asking at what time this function is a minimum. Well, the minimum value of the function is right here. You see what I'm saying? So how do I find the minimum value of a function? Well, to find the minimum value of a function, you take the derivative and you equate it to 0. So let's take the derivative of this one. That's going to be 2x minus 6, and you equate it to 0. And then you solve for x, and that will give me 3. There it is. And that's exactly what we got in the graph. So this x value here is 3. Now, I want to go the corresponding y value. That's easy. You just go back to this original function. So f of 3, and that will give me, what is it? 9 minus 18 plus 5. Did I do it right? 3 times. Yeah, that's going to be minus 5 plus, minus 9 plus 5, and that'll give me a negative 4. So so basically the point here would be 3 comma negative 4. I forgot what it is in the graph. Is that what it is? Is that what we got? Yeah, 3 negative 4. Okay, that's basically what he's asking me to do for our physics problem. Again, you need, the solution really comes from the basic calculus that you have studied, like this one here. Okay, so what I want to do first is I want to find the velocity function, and then I'm going to equate it to 0, just like I did here. So find the equal velocity function, which is basically velocity function is, by the way, you can write dx dt, or we can write it as x dot. In physics, the dot means the time derivative. So anyway, so we have here v sub x is equal to 6x t squared minus 12t equals 0. There we go. And then we solve for that would be so when I solve for t here, divide both sides by, divide everything by 6, I'm going to get t squared minus 2t equals 0. So t minus 2 equals 0. So t equals 0 and t equals 2. Now what is that? Well, these, I forgot to put a second here. This is where the displacement, the x here, is a minimum. So x is a minimum, or the displacement function is a minimum. X of t is minimum at those two values, at t equal 0 and t equals 2 seconds. Okay? But he's asking for what is the value, at what time v is minimum. So what I want to do, I want to get the velocity function, which I already got here, and then take the second, the derivative again, just like I'm doing here, but now this time for the velocity. I hope you understand that. So now I have the velocity function, Vx is equal to 6t squared minus 12t. So minimum at dvx dt equals 0. Okay, so you take the derivative, the second derivative, and that will give me 12t minus 12 equals 0. So t equals 1 second. That's so at t equals 1 second. Sorry, I'm running too fast. At t equals 1 second, v sub x is a minimum. Okay? That's the meaning of it. Okay, this is part A. Now he's asking for, what is that minimum value? What is v min? How do I do that? Well, all you need to do, you take that t equals 1 second, and you plug it into the velocity function right here, okay? So I go v min of 1, so you get the velocity function is 6, 1 squared minus 12 times 1, and that will give me 6 minus 12, and that will give me negative 6 meters per second. Got it? Okay. And the last part, sorry, I keep going back. Here we go. At what time A is 0? Okay, what is A? A is acceleration. What does that mean? Well, acceleration is basically the derivative of the velocity, which we already got right here. This derivative of the velocity right here, let me put it in a different color. This one right here, that's really the acceleration. Or this it's equal to 12t minus 12. Let's go back. He said what? He said, at what time A is 0? Well, make it equal 0, and then you just solve for you solve for t. So the way you do it, you go, okay, b, so dv dt, which is the acceleration, and that's equal to 12t minus 12, is that right? Sorry, yeah, 12t minus 12. Equate it to 0 and solve for t, and that will give you 1 second. So at this, A is 0. At t equal 1, A is equal to 0. Okay? Okay, good. I am going to move on now to the next topic in our lecture today, and that is free fall. Now we come to free fall, which is the second topic of this lecture. free fall, FF. Free fall means I have an object that is falling towards the earth or toward the center of the earth, and the only force on it is the force of gravity. That's it. All right, so suppose I have a height that looks something like that. Here is the object. Let's say I'm holding it between my fingers, say a ball, and I let go. Here is the height. Let's call that y, for example. And so it falls. So now it's falling to the floor, okay? It's actually falling toward the center of the earth. Yes, it is falling to the floor, but if you extend this line, it goes all the way to the center of the earth. Anyway, so it's falling, and if the only force on it is the force of gravity, there is no other force on it, then we say that the object is in free fall. Okay, that's the meaning of free fall. And suppose that we know the height of the object initially, so this height y, and we know that the initial velocity, say 0, because I'm holding it between my fingers, and then I would let go. Suppose that I ask the question, what is the speed of the object as it is falling down at, say 1 second, for example, or 2 seconds or whatever, okay? What is so because the object is falling in free fall, and it's under the force of gravity, and gravity has an acceleration called the acceleration due to gravity, g, and it's equal to 9.8 meter per second squared, okay, second squared. That's the value of acceleration due to the earth, right? So it's accelerating. So I can use kinematic equations, the equation that we just used, to find, say, the velocity of the object, the velocity, this velocity here, okay? So what I want to do now, I want to write the kinematic equation that we have just dealt with, but I want to kind of customize it specifically for free fall, and they become what we call free fall kinematics. So how do they look like? Well, V equals V naught minus GT. V squared equals V naught squared minus 2GY. And Y equals V naught T minus 1/2 GT squared. Okay? This is the notation that I use for free fall kinematics. All right, again, we're going to call them equation 1, 2, and 3. So the reason for the minus is because as the object is falling, go back to this diagram here, as the object is falling, the acceleration due to gravity, g, this one here, is always pointing downward, right? So you want to put a minus sign on it. So I just put it there such that g is equal to 9.8. Okay, don't put a minus sign on the 9.8. The minus sign is already in the equation right here, explicitly shown. Okay, the y here is basically the height, and everything else the same for the time and so on. And so that's basically, it's the same as the kinematic equations that we dealt with, but these are specifically the notation have been changed to fit free fall. So what I want to do now, I want to give you a simple example, show you how we can apply those free fall kinematics for simple situation. Then we'll do something a little bit more complicated. So here is an example for you. Suppose I am standing on top of a building. Hold on, let me just draw it here. I need some height. Okay, suppose I'm standing on top of a building or on top of say a hill or something like that. And what I want to do, I have an object in my hand, and I want to throw the object directly upward like that. And what's going to happen to it is going to go up, reaches a certain height, and then it's going to fall down to the ground here. Okay. Okay. Suppose that the height of the building or the cliff or whatever it is 50 meters. And the initial velocity of the object here, the moment I projected it or shot it up, is say it's 20 meters per second. Okay. And there are 5 questions. A, at what time the object reaches the maximum height? Okay. And part B, I'm going to write down all the questions. What is the maximum height? And C, the time to return to the level of the thrower. Remember, this is the thrower is right here. Right here. So the time to return to the level of the thrower, which is right here. Instead of saying that's the level. So time to return to the level of the thrower. And D, the velocity at this instant. And I mean, I'm talking about the level of the thrower, that is. Okay, and then the last part is velocity and position at t equals 5 seconds. Okay? That's basically what the problem is. It's a simple problem. But what I like about this problem is kind of a comprehensive problem. It, it has 5, it's asked for 5 or 6 kinematic variables to calculate, and so it got to give you a good understanding of how to use free fall kinematics. Okay, so maybe you want to pause the video and write down all of that and draw the diagram, because we're gonna move up. So the first part of the problem, it says the time it reaches the maximum height. Well, we go back to the free fall kinematics. Here they are. Let me draw them again. V equals V naught minus GT. V squared equals V naught squared minus 2 GY. And Y equals V naught T minus 1/2 GT squared. There they are. And so I want to know the time it takes to reach the maximum height. So I can use, so he's asking for time. So I have 1, 2, and 3. Only 1 and 3 have time. And so I'm going to use the first equation. V equals V naught minus GT. Now, at maximum height, what's going on with the velocity? Well, it's 0, right? I mean, that's why it stopped. It stopped because when something reaches a maximum height, it stops. If it's not 0, it will keep going. You still haven't reached the maximum height. Make sense? So what you do, you impose 0 here on this equation, on V right here, and that will give you immediately, will take you right to the maximum height. So it becomes 0 equals V naught minus GT. So T is equal to V naught over G. Again, solve the equation symbolically before you plug in numbers. And then we have here 20 divided by 9.8. And then the time would be 2.04 second. So in other words, at 2.04 second, the object reaches the maximum height. Let me go back in the drawing. The maximum height is right here. Okay, that's the maximum height. So how long it will take it to go from here all the way here? You see what I'm saying? And this time is 2.04 second. And then he's asking for what is the maximum height. Basically, you can measure it from here, or you can measure it from the floor, the ground, whichever, okay? I'm going to call this Y1 and Y2. Okay, and so what I'm going to be doing, I'm going to be measuring it from y1 right here. I'm going to call that maximum. How about that? Okay, we're going to ignore that. Okay. Now part B, he says find the maximum height. Okay. So which kinematic equation do I use? The logical one would be the third one right here. If I put in the time right there and right there to be 2.04, that will give me the maximum height. Make sense? So let me do that. So I have here, again, always write down the equation first. So y equals v naught t minus 1/2 gt squared. And the maximum height would be v naught is 20 times t, which is 2.04, minus 1/2 times g is 9.8 times 2.04 quantity squared. And we would calculate all of that. That will give me 40.8 minus 20.339, and that will give me 20.4 meters. So the maximum height, measuring it from the level of the thrower, okay? Measuring it from the level of the thrower here. Now, if I want to know the maximum height, measuring it from the ground, well, I just add a 50, instead of saying. I mean, this is 20.4, and then you can add a 50 from the ground. He didn't really specify, but let's suppose that from the level of the thrower. It doesn't matter. All right. Part C. He said the time to return to the level of the thrower. Now, if you think about it logically, you can probably come up with the answer immediately. There is some kind of symmetry going on here. The time it takes the stone, for example, or the ball, whatever, to reach the maximum height is exactly the same time it will take it to come back to the level of the thrower, because there is a symmetry. It's like this is an upside down parabola. Okay, so if I know the time it takes to reach the maximum height is 2.04, so that's another 2.04 here. So the double that would be what is it, 4.08 or something like that, and that will be the basically you'll be done. Or we can act like we don't know, and then we can use the third kinematic equation. Let me use the third kinematic equation. So there are two ways to do it. One way is basically 2t, just 2 times 2.04, and that's 4.08 second, and that's it. We're done. This is the time. The second method is you use the third kinematic equation, y equals v naught t minus 1/2 gt squared. Why do I use that? Well, at the level of the thrower, what is y equal to? The height. Remember, go back to the drawing. We started here. As far as the thrower is concerned, the height of the ball here is 0. Okay, I'm ignoring that. I'm ignoring the 50. To the level of the thrower. So it started at 0 height, it gained height, and then it reaches maximum, and it comes back to the level. So here the y max is really 0, if you will. See what I'm saying? So y here is equal to 0, and then I'm going to ask the question, when would this happen? You got that? So I go back to this equation. So I have 0 equals to v naught t minus 1/2 gt squared. And all I need to do now is to solve for time. You got it? So I'm going to solve for time. So I have here 0 equals 20 times t minus 1/2 times 9.8 is 4.9 t squared. And then I have a basic algebraic equation that I can solve. I don't need the quadratic formula for it. I can do it without it. And then when I work it out, you end up with t equal to 20 over 4.9. So t equal to 4.08 second, which is basically what we have predicted when we used just our common sense. Okay, that's just using common sense here. Okay, Same thing. Okay, good. Part E, or rather D, he said the velocity at this instant. In other words, what is the velocity of the ball right here, this velocity? Well, again, if we use common sense and symmetry, it should be equal to V naught. Make sense? So we have V equals V naught minus GT, and he's asking for the velocity. And well, what is the time by the time it reaches the level of the thrower? It's basically 4.08, so I'm going to plug it here. And we know the initial velocity, so V equals to 20 minus 9.8 times 4.08. Excuse me, and when we calculate that, it should be equal to 20, but I want to be careful here. 20 really, or negative 20, because we're talking about velocity here. So it is, as you can see, this is initial velocity is up, and that's why it's positive, but this one is going down right here, so that should be a negative number. It should be negative 20. My common sense should tell me it's negative 20, and which I think we are getting that. So it's going to be 20 here minus 9.8 times 4.08, and that will be equal to, let me look it up. I just want to get the exact answer. 4.8 times 9.8 equals 39.98. And that's basically negative 20 meters per second, which is exactly what we predicted because of the symmetry. All right. There are a lot of problems in physics where you can actually get the answer just by looking at it, just by, appealing to the symmetry of the problem. You know what I mean? Okay. Part E, he says, what is the velocity and position on the 5th second? Okay. So all you need to do, again, we can use the first equation right here. Put 5 seconds here, will give you the velocity. For the position, same thing. I can take, this is the position right here, or this one, it doesn't matter. And then you get this, and then you put in 5 here, and it will give you the value. So let's do that. So for part E, and that will be, here we have V equals V naught minus GT, and that will be equal to 20 minus 9.8, that's G here, multiplied by 5 seconds. And when I calculate, I get negative 29 meter per second. The negative here has a big meaning. It means it's going down. Okay, it's moving in the down direction. You know what I mean? Remember, this is a velocity, not a speed. And then what is the corresponding y? So I go v naught t minus 1/2 gt squared. Again, plug in everything in there. That's going to be 20 multiplied by 5 minus 4.9. 4.9 it means half times g is 4.9 times 5 squared. And then I calculate that, and I get negative 22.5 meters. What's the meaning of the minus sign here? Y equals negative 22.5 meters. What's the meaning of that? Okay, the meaning of it is this. Let's go back to the diagram right here. Pay attention, this is important. Let me use a different color so you can understand. Since I'm done with the problem, I can scratch it up. So what I have in here, see, the stone or the ball was projected from here, right? So you can think of it like my datum. Datum means x and y axis, if you will. The word, it's a good word to know, datum. I think it's singular of data. It means reference. Okay, so my datum x and y is right here. So if this is the y-axis, all right, So any measurement on the y-axis below it is negative. So this means this 50 really is negative 50, not 50. I should have put in a minus sign there. You see what I'm saying? So anything, any value of y that I measure down here should be negative. Well, I get the final answer to be what? Negative 22.5. What does that mean? It means if I'm going to be measuring it, what that means is the following. I threw the ball. Let me do for yet a different color. What that means is the following. Let's say I throw the ball up here. Here's the ball. It goes up. On the 2.04 second, it reaches the maximum value, right? At here, when on the 4.08 second, it reaches the level of the thrower. Well, on the 5th second, it's somewhere here, and it's going down. This is on the 5th second. Okay? I mean, part E here said the velocity and position on the 5th second. So what is the velocity here and the height? The position is basically the height, okay? Well, remember we said the height is always measured in negative because it's below the datum here, okay? It's negative. So we should expect a negative value for the velocity because it's going down. See the direction of the vector here, down, which we did. Look at that. We got the velocity to be negative 29. And the height here, or the position of it, should be equal to negative 22.5 on the 5th second. The negative here, that. You got it? Everybody got that? Okay. Okay. I'm having a second thought on the height here. The y equals negative 22.5. Where am I measuring it from? I'm measuring it from the level of the thrower. Remember that. I don't want to make a mistake. I think my drawing here is incorrect. What I'm trying to say is we started from here, right? We started right here. And then on the 5th second, so it goes up. Let me just do it. So we have a 5 seconds and it's come down. It is now the height here, the net height is 0. So it's going to come down here by negative 22. So the height that I'm measuring is not this one. I'm wrong here. The height should be this one here. I hope this makes sense to you. You see what I'm saying? It's the height, and of course it's below the datum, and therefore it's a negative. Okay, we're not measuring it from the bottom here. We measure it from the level of the thrower. Okay? Okay, good. The next problem. I like to call this problem the window problem. A little bit difficult, not terribly difficult. What you have in here, let me make the drawing first. It requires some thought. Anyway, so what you have in here, I need some space to draw it. Imagine you have a window, okay? Here's a window. And this window belongs to a tall building. Here's the frame. Let me just give me a time to draw the window. Now, the window belongs, it's part of a tall building. Imagine you have a tall building. Here it is, very tall building, you know, skyscraper. And the window is here. And this window is the one I'm drawing right here, all right? That's the window, okay? And okay, suppose that the height of the window, is 2.2 meters. And what I noticed, let's say I am outside the window and I notice there is a stone that travels the distance of this window, or the height of the window, from here and here, and it continues on. All right, so it continues on. So let me just write let me write down the statement. He said stone falls and takes 0.28 seconds to travel past a window 2.2 meters tall. Okay? Here's the question. From what height above the top of the window did the stone fall? Okay? In other words, the stone was thrown from some height, unknown height here, say the roof of the building, right? And this height that we're talking about, let me call it, say, Y1. All I know is that it took the stone to come from the top of the window to the bottom of the window, a total time, delta t, if you will, of 0.28 seconds. Okay, that's the only information that I know. And well, I also know the height of the window. So now he's asking the question, from what height above the top of the window did the stone fall? You get that? Okay. So you can pause the video and think about it. Like I said, it's not a terribly easy problem. It's not a trivial problem. That's what I mean, like the previous one. You kind of need to sit down and think about it. So, but I'm going to solve it for you. So the way you do it is, let me call this 2.2 meters is Y2, because I have this one to be Y1, the unknown, the one that I would like to know. Now, we don't know so we know the height here. We don't know the initial velocity here, V1. Suppose that there is a velocity here. I'm going to call it V1, but we don't know what it is, okay? We don't really care about the velocity here because it already left the window, okay? We don't care about that, but we don't know what this is. Now, because the stone was thrown from the top of this height, unknown height, so we can assume that this height, the initial speed of the stone here is 0. Make sense? When the stone was here, the initial speed of the stone is equal to 0. All right? Okay. Let's look at, so what we want to do, I want to use a kinematic equation to solve the problem. I hope you have already drawn this in your notebook before I make it disappear. Let's look at Y2, which is the height of the window, and use kinematics. Remember, the stone is falling in free fall. So I'm going to use the third kinematic equation. Y2 equals to Vt minus 1/2 gt squared. Now, what is this t? T is the one that is given to me, this one. Maybe I should just take this delta out. This one right here, okay? And the v here is the initial velocity. Remember, y2 is this one. So what is the initial velocity? Well, it's just v1, right? I mean, v2 here, whatever it is, it's larger than v1 because it's accelerating, it's falling. So the initial velocity as far as y2 is concerned is really v1. I don't know what it is, but the good news is what? I know t, and I know y2, and from there I can find v1. You see the trick? Okay. So I'm going to plug in my numbers in there. So I have here, but I want to be very careful. Now, the stone was thrown from here, right? From here. So that means anything below it is negative height. Remember we talked about the datum? So that's negative height here. So you want to be very careful. So the height y2, which is the height of the window, is going to be negative 2.2 equals v1 times the time is 0.28. Is it 0.28? Yeah, 0.28 minus 1/2 times 9.8 times 0.28 squared. There we go. Okay, so from this information I can find the velocity of the stone right at the top of the window. You know what I mean? So by working it out, so I have minus 2.2 equals to 0.28 v1 minus 0.384, and then you solve for v1 and you end up with negative 6.49. Now I'm not surprised by the minus sign here because it's a velocity and it is in the down direction. So I'm not surprised with the minus sign here. It is expected actually. Okay? Okay, good. Now I know that. Well, what else I can do? Now remember, I need to find v1 right here. Well, think about it. If this is the initial velocity here is 0, now remember I'm in this region right now. So in this region, what's going on? The initial velocity is 0. The stone was thrown from some height, you know, say the roof of the building. Okay? And I know it's 0. And the final velocity right before it's at the top of the window is v1. I already found it. Well, I can use kinematic to find y1. Which kinematic? The middle one. The one that doesn't contain time. This one. So now we have v1 squared. Let me put it here. Let me put it down here. V squared equals v naught squared minus 2gy. This is the general kinematic equation, the middle, number 2. Okay, if you go back, that's number 2. This is the initial, and that's the final. The initial for us is 0, v naught, right? Stone started from 0, and the v here is 1. So v1 squared equals to v naught squared minus 2gy y1. Okay, y1 is basically the height from which the window was thrown, right here. Okay, I hope this makes sense to you. All right, so this v naught squared is 0, and I have everything really. I just need to find y1, so that will be equal to v1 squared over minus 2g, and all I need to do is to plug it in. Of course, going to get negative answer, which is expected. So negative 6.49 squared divided by 2 times, I'm sorry, I made a mistake. Parentheses negative 6.49, that's what I wanted to do. With a minus here because of this minus, 9.8. And then when I plug it in and calculate it, I'm going to end up with negative 2.15 meters. And there we go. Why is it negative? Because it's below the datum. Here we go. Here is my datum. Let me make a drawing again of it. Let's pick green. So here we have, here's the datum right there. This is y. So anything below the datum, the origin here is negative. Y is negative here. See what I'm saying? And that's why we keep getting those y1 and y2 are negative answers. So we get them there. And there we go. We have it. Okay? I hope this is clear. I think I'm going to stop here. That's the end of the lecture. Next lecture is going to be on vectors, which is the mathematics topics, and kinematics in 2 dimensions, projectile motion. Bye-bye.